Hey class, Mr. Moyden here with a help video on a calculus topic, this time the area between two curves with horizontally oriented rectangles as opposed to our vertically oriented dx rectangles. This time we're looking at dy. So the question here would be, what is the area of the shaded space or the shaded region? And if you first look at it, you'll notice that these two curves are not functions. They fail the vertical line test. And moreover, if you actually draw that vertical line, you can kind of see that finding the area of this particular region would be kind of funky, and especially as I move closer this way, you can see that the same curve is represents both upper and lower boundary. That's a clue that maybe a different perspective is going to be needed here. So if I draw a horizontal rectangle, that's going to be representative and useful because it tells me that my boundaries are one of my parabolas sort of facing its side, and as well as this other one. And that holds true no matter where I make this rectangle, right? The boundaries remain constant. So a single integral should find me the area of this region. The paradigm is the following. It's the integral from lower boundary to upper boundary, where keep in mind these two numbers here are limits of integration are going to be y values that basically tell us from where to where do we go with these little vertical slices. So if it's not already given, sometimes you have to do a little bit of algebra to find it. Here it's a safe assumption that it's going to be -4 and for the lower boundary, and all the way up to 2 for an upper boundary. If you want to be more precise, what you can do is simply set these two statements equal to each other and solve for y, and you should find those two answers, -4 all the way up to 2. But in this case, it's a safe assumption there. Our actual paradigm, though, is right function minus left function. So let me try to illustrate that the best I can with some color. Here I have this parabola in red, and I have a secondary parabola here in yellow. So, a couple ways to figure out which one's which. The fact that one of them has a leading coefficient that's negative is a clue as to which one it is, but if you're not sure about that, you can also use the x-intercept. If I plug in y equals 0, I get -5, and the function that has a y-intercept of -5 appears to be the yellow one, so this one would correlate here. And likewise, a y-intercept of +3, if I cover up that business, plug in 0, an x-intercept of +3, and you can see that would be the red function here. So I'm going to use orange on this portion because you can't really see the yellow on the white. The paradigm is right minus left, or larger amount minus smaller amount, to give me the width of each one of those green rectangles. We'll talk about the height in just a moment. So the red boundary, or the right boundary, which is made by the red curve, would be -y squared over 2 minus 2y plus 3. So right minus the left curve, which is the lower boundary, the lesser value rather, which is y squared minus 5. I'm going to use parentheses here deliberately. Y squared over 2 minus 5. So this entire red and orange statement represents the width of my rectangle for any given y value. So for example, here I have a y value of looks like roughly 5-ish or so. If I plugged in y equals 1, which is where this is, I would get that value. If I plugged it into all of this green business right over here. So that's basically what that means. So that's going to be the width of each rectangle. Of course, rectangles are two-dimensional. They have heights as well, and the heights here are infinitely thin slices called dy, or sort of an infinitesimal version of delta y. So let me do that here in blue. That's dy. So base times height, or height times length times width, whatever you want to call it, the rectangle's area would be found by the green portion that I've underlined times the blue. And if I sum these up, I have the exact area because they're infinitely thin. So let me see if I can simplify my integrand here, which is the underlined green portion. The area, or the sum of rectangles from -4 to 2. If I distribute that negative over there, slowly inch my way there, I get -y squared over 2 plus 5 dy. I can simplify further. Let's see, I have a -1/2 minus another half. It's going to give me a full -y squared. This is my only y term, is it not? So minus 2y. And my constants here, 3 and 5, will give me a plus 8 dy. So So now it's just a matter of integrating this thing as simple as it can get. So in terms of the integrand, so let's go ahead and integrate. So negative, and then third power up by 1 divided by the same number. Same thing basically here, although I know it's going to be y squared. It's a familiar antiderivative. And this will give me 8y from negative 4 to 2. So at this point you could grab a calculator and just do numerical integration or Math 9 if you wish. And if you want to skip to the end of the video here, you can. That being said, I like a good challenge at the end of the day, so let me see if I can get the exact answer without too much of a calculator. So the fundamental theorem of calculus tells us we take the antiderivative and we plug in the upper bound, and we plug in the lower bound, and we subtract those values to get us the value of the definite integral. So populating my integration here, I'm going to get 2 cubed, which is 8, minus 2 squared is 4, plus 16. Let me see if I can simplify that before I get to the next portion. That's going to be negative 8 thirds minus 12 thirds plus 48 thirds. Negative 8 take away 12 is negative 20. Plus 48 will give me positive 28 thirds for that portion there. Doing the fundamental theorem here, let me remove the lower boundary. Keeping in mind that it's a negative 4, that's going to be a little complex. Let's see how that carries. Negative 4 cubed will give me negative 64. Already negative here, so it's going to become positive. Divided by 3 is positive 64 thirds. Sorry, negative 64. No, sorry, positive 64 thirds. Like I said, at the end of the day. Plug it in, negative 4 squared will give me positive 4, but I'm subtracting anyway, so negative 4 and negative 32. So, getting back into thirds here, 64 thirds minus 12 thirds minus, I believe, 96 thirds, if I multiply by 3 correctly. This is going to be a bit of a challenge. 64 take away 12 will give me 52. 52 take away 96. What's the difference in 52 and 96? Let's see, that'll give me 44, looks like. So it's going to be negative because I'm taking away more, so negative 44 over 3. I'm actually adding these, however, so let's see what 28 and 44 will give us. Well, 30 and 44 is 74, and then take away 2 to get back to 28. That'll give me 72 divided by 3. And 72 divided by 3 is one that I should know, but don't really feel like exercising that muscle. Looks like it's 24. Seems a little low. Looks like I've actually made a mistake here. It took me a moment to find it, which I paused for. This should have been positive, actually negative 16. Which will make this, apologies for the error, negative 48 over 3, 64 minus 48, 64 minus 48 is 16, I believe. So it's going to be 16, negative 16, sorry, 16 minus 96 will give me negative 80 over 3, which means I'm actually adding. So let me fix these. 28 and 80 will give me 108. 20 is 100, so ignoring this, 108 by 3 should give me 36. And if you count the number of blocks, you get closer to that, which is what I knew was a clue that my answer was off by a bit. So, moral of the story, you should probably use numerical integration, I guess, huh? Oh well. Hope this helps.